Hello, hello, Battlesnake friends. It's Aurora. I'm here to do another episode of Deep Learning with you folks today. So welcome. I'm so happy to see you all on this. I don't know where it is where you are, but it is a rainy Thursday for me. So I'm super happy to be like cozy with you folks, talk some code. This is a good day to just like hang out and have some light intellectual discussion, I feel. So happy to see you. So this is Deep Learning. This is the Battlesnake show where we kind of do a bit of like a deep dive into some of the more educational, interesting, nitty-gritty details of Battlesnake, which is a fabulous game. I'd like to open up by thanking our 2021 annual partners. So thank you highly to AWS, to RBC, and to Replit. Because of them, we're able to do shows like this one. So we're very happy for your support. So thank you to our partners. And if you have seen Deep Learning before, if this is like a comfortable place for you and you've been thinking about a topic you'd love to have discussed or reviewed on the show, let me know. Maybe you know someone who's done something interesting and they'd like to come come hang out on Deep Learning and hang out with me and maybe talk about what they've built. I did a great episode last time with Penelope Zone. We installed like monitoring and observability into our Battlesnake, which was very cool. And it was super awesome of her to take us on that journey with her. So, just an example. So today I thought we would cover kind of like those early algorithms that really help in building your Battlesnake. If you're, just sort of starting out and you're kind of exhausting what you can do with an if-else statement Battlesnake. You're checking the walls of the arena and you're like making sure you're not colliding with them and you've got some like basic collision detection happening. But how do you start like setting that up to the next level? How do you start like looking more than your next square move? So those are the kind of like helpful algorithms. Just kind of do like a primer and talk about what they can give you and what can sort of help out in that early stage journey. Which I think is nice. This is a good video to put in the archives, right? Just like your reference for when you want to start exploring stuff. So yeah, feel free if you have used any of these algorithms or tried anything different or done something weird that you'd like to share, pop it in a chat. Let me know. I'm happy to talk about it some more. But let's definitely dive into those useful Battlesnake algorithms. So what I'm going to do here, I'm just going to like bring up a game here. I picked one from Fall League just to sort of like start talking about this, right? So this is like a early match. I can't remember if I think this is elite game, but just sort of like looking at some Battlesnakes on the board and like kind of thinking through, as humans do, what could possibly happen here and like what are some objectives or things we could go to. So we've got 4 Battlesnakes on this board. This is a Royale game, so hazard sauce is going to creep in here. But like even just in the starting like initial position for your Battlesnake, like what are some things you might want to do? What are some like first step areas you might want to look into? So probably one of the first things, like if you're following like the Battlesnake Challenges guide, I'll just crack that open here for a second. It's got like what I consider to be the first 4 commits that every Battlesnake should have. So like when you're building your Battlesnake for the first time, this training program was designed to guide you through that process. So the first one is avoid walls, which you can kind of like hard code more or less, right? Like you can look at the data you get from the Battlesnake engine and you can find out where the walls are and be like, okay, like don't go off. Like I know I've got my XY coordinate system. So that one you can sort of like hard code in. Avoiding yourself can be sort of like a lookup, like seeing where your body segments are, seeing how long you are, and just avoiding moving into a square that's already occupied by you. Same with avoiding other Battlesnakes. But find food is where it really starts to get interesting because like, how are you going to go about doing that? Like how are you going to find food and how are you going to get there? And like, what are the different ways to get there? So when I pop back to this like Battlesnake game board, like one of the early rules of Battlesnake is that there's always like a food spawned in the middle here. And then there's always a food that's like one away from your head. from your Battlesnake's head. So like that's kind of like the first thing you can do. So it's one a way. So there's only like a couple ways to get to it. But what we see it a lot in Battlesnake games is like after Battlesnakes have eaten that first food, there's kind of like a race to the center piece as well. And then the question is like how you decide to go there. So I'm going to start dropping some keywords here. If you're early in your Battlesnake journey and you're like, okay, what are the things I even Google to know what I want to look at and learn? I remember that like my early days being a programmer, sometimes the hardest hurdle to jump over was just like, what's the keyword I need to learn about a concept I can describe, but I don't know what it's called. And that's like the first concept I want to talk about, which is pathfinding. So pathfinding algorithms are a really great way to start. And like, once we have a destination in mind, like we know where we want a Battlesnake to go, what are the different ways we can sort of guide it to go there? So for this Battlesnake, like if we take a look at Hoth in the corner here, I mean, after picking up this food or not picking up this food, might want to like try to zero into here. And we can go like a couple of different ways. Like we could zigzag up, we can go across. So what are the different like pathfinding algorithms we could take? Another thing to consider is if you have a Battlesnake who's maybe a bit aggressive, you might want to pathfind to like other Battlesnakes' heads or try and like chase them. Chasing another Battlesnake's head, even though that's a moving target, that's something you might want to do kind of like deliberately going for that. So you have like a specific XY location, you know, that's maybe the head of a Battlesnake, and you might want to go for that on purpose. Or you might be deliberately trying to go for maybe kind of close to the edge of the board or like a specific location. So if I just step through this game a little bit, so we've got some Battlesnakes moving. I can see Prusi's picked up their food. Hoth is picking up that like little corner, like little food that spawned luckily in front of them. And it kind of looks like we have 3 Battlesnakes here who are now pursuing the center food, which is pretty classic. Looks like Fleur de Lance in the tan is moving away. And we just got people moving, and eventually Prusi actually picks it up here. So these Battlesnakes are pretty small. You know, there's not too much going on. There's maybe some hazard sauce, a little bit of avoidance of diving into it. And where this gets interesting, just kind of like looking at the types of problems we might want to solve, is in a high-level game like this one, you might have a lot of Battlesnakes on the board, and they might get kind of big. And you might start getting into situations. So I'm just going to highlight Fleur de Lance here in this particular shot. So in addition to like pathfinding and deliberately going to a specific location, another problem that pops up pretty quick once you've sort of exhausted your if-else statements and like straightforward rules is trying to decide if you're going someplace that's going to trap you. So that's why I'm kind of highlighting Fleur de Lance here, because if we look to their left, there's quite a lot of like open space. Fleur de Lance is like length 9 right now, and like maybe turning left could be an advantage over turning right. There are only 1, 2, 3, 4, 5 squares that are out of this hazard sauce, 7 that don't, and like just a wee little bit of space here. So if I advance kind of one more turn here, this is interesting. Sort of starting to get cut off a little bit here by Prusi. And this really seals the deal. Now Prusi has come in and kind of like blocked off a square. And this is like a totally, there's only like one fill zone here to go. So this comes kind of like to our another type of algorithms. And it's kind of like looking into our space and seeing how much space you have to go. And one we'll talk about a bit more in a bit is flood fill is really popular for doing that. So those are kind of like the 2 classes of Battlesnake algorithms I want to talk about today, is these sort of pathfinding and these like fill algorithms, and sort of see like what are our options and what could we experiment with for these higher, like, you know, for your like leveling up your Battlesnake. We're not totally getting into like aggressive machine learning AI here yet. This is kind of like a nice transition phase to like add some extra logic and some extra decision making to your Battlesnake. So yeah, poor Fleur de Lance gets knocked down because they got squeezed down here by Prusi, and just sort of seeing how this game goes. I think flood fill, as long as you can distinguish between the hazard sauce and like non-hazardous areas on the board, that can also be very helpful in understanding the size of, how much space do you have to move in that's safe versus kind of like a little bit dangerous. So I think that's another great application for that algorithm. And just running this game out here. This is from Fall League tournament. 2 big Battlesnakes, highly skilled here. Pruzy eats it. They ran out of health in the sauce there. But they also ran out of free safe squares to go into. So just an example of a game, sort of like get some like motivation for why you might want to like look into this. So I'm just going to swap over here. Switch to like a little drawing here, illustrative example of like something we could do and like something we could consider maybe for how to approach like our first pathfinding algorithm. So, I mean, maybe using the term algorithm's a little generous here, but like if you just kind of think about this problem constructively. So I have like a simple Battlesnake board here where I've got like a wee little Battlesnake down here and a single piece of food up here. And if I'm pathfinding and I want to like get to that food, I think this is a screenshot from the Find Food Challenge. So it makes it a little hard for you. A really, really simple algorithm you could start with is what I'm going to call direct. So there's sort of 2 versions of direct paths. So we know the x-axis, we know the coordinates of this Battlesnake. So this is going to be 0, 1. What is this? X-axis first. So it'll be 1, 1, I guess, is the location of the Battlesnake. And what's the size of this board? This has got to be the biggest. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's okay if I count, right? 10, 11, 12. Okay, 18. So this is the 19 by 19 board. So then that's going to be 18, 18 in the top corner. So if you know you're at 1, 1 and you want to get to 18, 18, you could kind of like take your x-axis location. Or like, if I'm at 1, I'm just going to go up until I hit 18. So to sort of like draw an approach here. What do I got here? I could just like go this way, right? I could just be like, all right, I'm going to go up to 18 until I have made my head's y value the same as the y value of my destination. And then I could increase my x value and do literally the same thing. And I could just go across here. And I would call that, I mean, it's not a sophisticated algorithm, right? But it's a direct algorithm. And that's something that would be fairly simple to code. If you already have a little bit of like Battlesnake avoidance. So, I mean, this works really, really well when you're alone on the board for sure. But when you have other Battlesnakes involved, you could still write that same code, like always preferring, like at any given time, this Battlesnake has, 3 choices. It can go up, down, or right. So when you're like, all right, if up, down, and right are all safe, I don't have a barrier or something in my way, I'm going to prefer going in the direction that allows me to increase my x value, and then I'll prefer going in a direction that allows me to increase my y value. And if you follow that, unless there's a barrier, then you'll get there. Like you'll sort of like move around. Another approach is like a zigzag. I couldn't find the game for it, but there was like a pretty hilarious RBC intern game where I think there's like 4 Battlesnakes just like zigzagging everywhere in kind of like a weird synchronized swimming kind of way. So another approach that we could take is you could just like alternate your increasing your x and y value until you got to where you were. So maybe you do y first, and then you're like, oops, moving this over here. Cool. So maybe you go x and you're just like, I'm going up, I'm going over, I'm going up, I'm going over, all the way until you get to your destination. And like, that's another approach too. And same sort of goal. You're just like moving to try and increase it and make it so your head location is now matching the location of where you want to go to. Because this right here is our destination. So I'd call these like super direct and could be improved with like a little bit of anti-collision logic. One of the downsides of this approach is you really need to pick where you're going in advance. So you already need to know where you're going. And I haven't described a metric for deciding that. Like at this point, I might just like look at the list of all food and take the first one. And it might be close and it might be far away. So like those are some weaknesses, but it's simple to write and it's simple to code up. And it shouldn't be too hard to go. So, just some sort of direct path stuff. So I'm explaining this really simple algorithm because I want to introduce one of the more sort of popular ones. And I'm just going to swap over here. So you might see people talking about this in chat, like in Discord, or like you might see it when people are writing about Battlesnake. But a kind of like more refined version of what I've just described is called the taxi cab or Manhattan distance. Most people in the Battlesnake community call it the Manhattan distance. And it actually does something pretty similar. So Manhattan distance is pretty popular. There's a lot of distance algorithms out there. If you Google, you'll see things like, so Euclidean, which is on this diagram, is this green line. So Euclidean geometry is like drawing the triangle, right? It is literally the shortest path measured distance-wise. But a Euclidean algorithm isn't going to work for a Battlesnake board because we're in a grid system. So we're not working in like just like a flat plane space. We actually have a grid. And that grid concept is really important to keep in mind when you're looking at algorithms that are out there and what's available. So let me just, share my screen here. Have an illustration for you of what this looks like. Here we go. Cool. So sorry, as I was saying, this green line here is like the Euclidean distance. So this is the same sort of idea as like if my Battlesnake's in the bottom left-hand corner and my destination or my food is in the top right. Green line, the Euclidean distance is literally the shortest, but it doesn't help us in Battlesnake because of the grid problem. Because we can only operate in like 4 directions. We can go up, down, left, right. We can't move on diagonals at all in the Battlesnake space. So what's interesting about this is, so Manhattan's distance is specifically applicable to grids, which makes it perfect. And it'll find the shortest path between 2 points. So this is helpful because you could take a Manhattan distance calculation, look at every piece of food on the board, and that will tell you which one is closest to you, which might be helpful. So if you're watching your health and you only have, say, 10 or 15 health, you need to get to a piece of food that is 10 or closer to you. So otherwise your Battlesnake will be terminated before you get there. So this is a really helpful algorithm, and it's fairly straightforward. It comes in a lot of libraries. I know in Python, the SciPy library, which has a lot of formulas, it has a whole library of distance calculations, and Manhattan distance is definitely in there. So if you're building a Python Battlesnake, that's available to you. But you'll notice too that like part of the options here, so here are 3 examples of paths that the Manhattan distance kind of recognize. And it's like, it includes what I described as direct, right? Either that following the XY axis, the jagged end, or yellow sort of describes kind of alternative routes. So if you kind of imagine yellow is moving around, say a bit of Battlesnake body here, you can sort of see it'll get you there. So Manhattan distance is super popular. Most people that I've heard of are using this, and it's very, very helpful. One downside, and this is not so much a downside as like a barrier or something you have to handle, is it really does not have any consideration for barriers. Like if there's a Battlesnake in the way, it doesn't take that into account. There's no input into this calculation that allows you to say, well, hang on, some of these squares I can't actually travel through. So Manhattan distance will help you determine maybe what's closest or what the shortest path is to your destination, but it can't, tell you that that route is safe or like available to you to use. So for this, you could use sort of basic Battlesnake anti-collision logic. Just don't move into squares that there's a Battlesnake segment in. And what you could do then is just kind of like keep recalculating every turn, especially since food appears or disappears. So you might want to change paths. So that's an option for you, and like a really common algorithm that pops up when people are talking about Battlesnake. So I want to talk about something a little more fun now. So there's some problems with Manhattan distance, but there's kind of a more fun option. And this is, if you have a computer science background or you've taken an algorithms course before, Dijkstra's algorithm. Dijkstra's algorithm is actually pretty applicable. It works a little bit different than this one. I've got a sweet animation. And shout out here to Wikipedia. Man, do I love Wikipedia. Like for technical concepts, it can't be beat. It's like a perfect starting place. I love using Wikipedia to like refresh myself or remind stuff. So Thank you, Wikimedia Foundation, for maintaining this wonderful website that I love. But let's take a look. I've got a visual here for Dijkstras. So the way Dijkstra's algorithm works, and this works in any graph and therefore works just great in our Battlesnake grid system. But what it does is it starts from like a source node. So this animation started in the bottom left-hand corner, and it starts to like explore moving up, down, or left, right. So we've got the same sort of movement here as our Battlesnake, and it tries to find the shortest path by building this like tree structure to a specific location. So it's going for the green dot. You can see it going here. There we go. Okay, it found it, and this green line gives us the shortest path. And a huge advantage that Dijkstra's algorithm gives us here is that it handles barriers and it handles places you can't go. So you can provide as input not only your like starting points, so your Battlesnake's head where you are right now, and the destination, maybe a piece of food you're going for, but you can also supply it with the locations of other Battlesnakes, and it'll produce a path that goes around them, which is pretty dang handy. And like barrier in this case could mean a lot of things. Maybe you're building a Battlesnake where you deliberately want to avoid the hazard sauce, or you want to run a calculation without moving into the hazard sauce, or you're just looking at various barriers, whether it's other Battlesnakes or something else. So this is very, very helpful and handy. And it's what it's doing here in its calculation is it's producing a tree essentially, and it just continues to explore and calculate the distance and like branch out until it can tell you what the final path is. As you might imagine, it's just a little bit computationally expensive. I don't know of anyone specifically who's trying to run just raw Dijkstra's algorithm in their Battlesnake. If you are or have ever tried that, please let me know. I'm very curious. I should try it myself, really. But I feel like this might be like a little challenging to run every turn within the 500 millisecond time limit. So this might be a barrier. But I want to include it because Dijkstra is just like an icon in computer science history. So if you haven't heard of Dijkstra, look him up. He was a very famous computer scientist, a very quotable computer scientist with very strong opinions. And I think he died just in the early 2000s. So there's a lot of great quotes and writings about him, which, total aside, that's like one of my favorite things about computing science is it's such a young industry. Like you can like meet people who are highly influential because many of them are still very much alive and out there and building stuff. So that's something that's very, very cool. And Dijkstra is definitely one of those like pillars in computing history for sure. Cool. All right. So this is an improvement. Like when we're talking about iterating our Battlesnake, direct, simple, straightforward algorithm to code is pretty good. Manhattan distance gets us something just like a little bit better. And Dijkstra's is much better at hitting this barrier and this path. But it's still, computationally kind of expensive. So that's going to bring me onward to the next algorithm. And this one's very popular. Everyone talks about using A star. And I have an algorithm. So remembering this like Dijkstra's fill algorithm, A star is really, it's kind of like an extension or a more efficient implementation of the core concepts of Dijkstra's algorithm. Much more efficient in its search, which is why it's a popular Battlesnake algorithm, right? This is definitely one. A star is definitely something you can run in your Battlesnake server within the 500 millisecond. So thanks to the fine contributors at Wikipedia, there's actually an algorithm that's identical to this one's identical to the Dijkstra's animation. Let's see if I can get it a little bigger here. But it's a little bit different. So we can talk about how A star operates just a touch differently here. So Dijkstra's algorithm started from a root node and extended to all nodes in every direction, just like without prejudice. It just went. But what A star does is it tries to evaluate which path it's going to extend instead of doing them all. So it's like trying to pick ones that it thinks are doing better already. and it'll just like keep going until it finds an answer. So it also halts as soon as it reaches the destination. It didn't continue filling the board. So it's got the same sort of benefits. It can handle barriers. So if that gray L shape there is, if you imagine that being a battlesnake, like it's figuring out that there is a path around, and it'll like get there. One of the downsides of A star is that like, because it stops as soon as it finds the destination, depending on how it's configured, it might not actually find the like literal shortest path. There's like a possibility there's a shorter path. But what it does tell you is that there is a path that is decently short. And given the problem space of Battlesnake, that sounds good enough. Like we don't have to achieve perfection here. So I don't think that really matters within the Battlesnake problem space. And just to sort of like illustrate that, here's a different animation that like focuses, it highlights which branch it's going and kind of shows a little bit better that it's a tree structure. There we go. So very, very similar and with like a lot more sort of scattered barriers. So the black dots are barriers that you can't go through. The red are nodes or locations on the grid that it has looked at. And the blue line is like the path that it thinks is the best right now. It's like the path that it's exploring. So same sort of thing. You can see it's not extending all the way to the edges, but it's finding its way from the top left-hand corner to the bottom right, its destination. And you can like, I like this one because it really illustrates how it's storing its data as a tree. It's understanding, and it's got this blue branch is the path that it's currently exploring. So when all paths are equal, like it is here, it's just kind of iterating over them, being like, okay, I extended it by 1. Is this any better? Is this any better? Until it sort of starts to narrow in on where it's going, which is very cool. So A star is really popular. A lot of people building Battlesnakes are using A star. And this is kind of a visualization of how it works. And whether we're talking A star, whether we're talking dijkstras, same sort of thing. These are algorithms that are already implemented in a lot of scientific libraries in most programming languages. They're very, very popular. So you should be able to find them. But I'd like to challenge you, if you're feeling up to it, this could be just a fun excuse to try building these yourself. And maybe this is like various flavors of fun. I definitely remember being in university and having to write on an exam like pseudocode for how Dijkstra's algorithm works. And it was just like an awful memorization, like practice of memorization, which isn't super fun. But this is Battlesnake. There aren't rules about how you interact. I mean, there's Battlesnake rules, but there aren't rules about how you choose to build and what paths you choose to explore. So this could be a nice application or a nice opportunity to practice hand rolling your own algorithms, seeing how it's built and giving it a go. Even if you have a high performing Battlesnake, maybe this is the time to do that like little bit of practice for fun. I mean, you could do like, I don't know, you could do like logic problems or algorithm problems on some website to prep. But I always feel like there's like a bit more of a personal investment if you're doing it for yourself, for your Battlesnake. So that's, that's an option for you if you want. I don't know. It could be fun. I feel like I would be more excited to write Dijkstra's algorithm in A star and do a comparison for a Battlesnake than for like school or something. But these are cool. Another benefit, this is true for both A star and Dijkstra's, is something that is definitely not obvious from this algorithm. So in this visualization, we're always getting to our destination, but there's a possibility you can't reach your destination. Like you might be cut off from other Battlesnakes, or the board might change. So, I mean, this can also help identify whether or not you can even get there, which is a good question. You don't want to be careening towards a piece of food, but actually careening towards a situation where you're going to get stuck behind a Battlesnake. Another thing is, like, we know as well that the Battlesnake board isn't static like this. So you will be wanting to run these algorithms every turn. So every turn you're going to have new input. What's the location of food on the board? What's the location of every Battlesnake on the board? So you would, when you were writing your code, you would want to sort of like rerun these algorithms each time. So you do want them to be snappy and quick. Cool. Awesome. Pretty quiet in chat today. That's okay. But if anyone's doing anything like this or thinking about this stuff, or maybe you have a different pathfinding algorithm that you're interested in, these are some popular ones. I'm sure there's more out there, but the big key is you want to look for things that have grids or graph. Like graph theory is a great place to be looking for algorithms that could help you with your Battlesnake building. Because I mean, most graph theory problems, you just sort of think of like nodes connected. But a Battlesnake board is really just a very uniform square set of connected nodes. So graph theory is where you want to dive if you're looking for things to help you out in building your Battlesnake. Ah, hey Taranemi, thanks for saying hi. Makes me feel less lonely. Cool. All right. So these are some pathfinding options. Direct, hand bomb a direct route, throw some Manhattan distance in there to give you a calculation. Try out Dijkstra's algorithm, helps a little bit more with barriers. And then A star, of course, the optimized version of Dijkstra's. So this is good for going to a specific destination. But what about trying to see whether or not a direction is going to lead you to a place where you have enough space? So this is where like fill algorithms really kind of come into play. So I'm going to show some games where this becomes important. Whoops. Cool. So I'm just going to pause this. Let's move forward. I think this is also Fall League. I'm just going to zoom through this game until we get to turn like 160. Okay. All right. So let's set the stage here. So we have Killer Whale on the bottom here. We have Ready, Set, Hike in the blue, football uniform up top. And they both have a lot of space right now, which is good. Killer Whale's in the sauce, so it's a little bit dangerous, but there's also a lot of food around them, so it's not too bad. Ready, Set, Hike is about to move into the safe white zone, which is slowly shrinking here. And if I just move through this a little bit, so this starts to get a bit interesting because both of them have turned in on themselves. And we can see right here, if you're Killer Whale, and you're kind of looking in each direction, you really only have an out if you start going back left, right? You're in a little bit of trouble. And same sort of decision making here for Ready, Set, Hike. So using flood fill and just sort of seeing the shape of this, there's not a lot of room for escape. So we do see Ready, Set, Hike turns right, moves into the space that's much larger, much more space, also free of the sauce. And we see Killer Whale turning right here. And right now they are in a closed off box. So they only have 3 squares of space available to them. Although if Killer Whale is really well programmed, they'll know that their tail is going to move and open up that space again for them, which they do. But we can sort of see this like little bit of tangling that happens. And I believe this happens again here. So yeah, I mean, and this is interesting. I think that Royale games are very interesting for doing fill calculations because you have some choices about calculating fill for the entire board or calculating fill for like the hazard sauce or even for the safe zone. And like maybe those are things you want to compare when you're thinking about, okay, if I move into this space, do I have enough room? Do I have enough room that's safe squares? How much damage am I going to take if I'm in hazard sauce only? So same sort of thing here. Killer Whale, if Killer Whale is doing any kind of basic fill, they should know right away that left is the safer option because there's a whole whack of space over here and right only has 3 squares and they are definitely larger than 3. So they make that choice. I mean, I think this is like a platinum game. So I expect those kinds of good choices. And unfortunately, even though it was the right choice, they didn't quite have enough health to get through there. But that's an example there. I'll do the same thing here. Let's take a look at another game. When I do intern tournaments, we see this a lot. Like people start hitting the point where they're like, oh, I need to like see if a place I'm moving is safe. Okay, oops. Here we go. So I want to start at turn 104 for this one. So we have 007. I think this is an RBC intern game, actually. I don't know how to use a computer. Poor little swirly-eyed dude down there. Random Snake and player 456, I think, had already been eliminated. Here we go. So just stepping through this game here. So these Battlesnakes would have been built rather quickly in just like a couple of weeks. So they haven't had as much time to mature as, say, in the games we've been looking at for Fall League. But taking a look at this, we see like 007 in the same sort of spot. So they could go down. There's not a lot of space, but they could tail chase. So that's an option available to them. And I don't know how to use a computer. Definitely has some danger. Up is a potential head-to-head collision, but down should be safe. But I think poor random snake here could have made, I mean, this is a tough one. This is an example of like a really tough situation in flood fill because you might not know until it's too late. But if they're taking a look, so flood fill, even here, if they look down, they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 free squares below. And they are of length, I can't even see because their name is too long, but they are more than 11 squares, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, they're way more than 11 squares. So like down is kind of a rough choice. Like once they get here, they can't really go any further. Like maybe you might be able to look ahead enough and say like, okay, I don't know how to use a computer. Tail's going to move out of the way, but they're also going to close off your entrance. So like if you're doing a flood fill calculation, this is a good example of looking at this and being like, that is too small for me. Even though down is a safe turn this turn, it is not a safe turn for the future. So I should move left. And unfortunately, this Battlesnake is not programmed to do that. And predictably, it just runs out of space and ends up having to collide because it's completely cut off by I don't know how to use a computer. So a flood fill algorithm in this case would have helped them, would have saved them, rather than sort of maybe a bit more random movement. Let's see here. Does this game have any more examples of this? This is kind of fun because like where this really tends to happen, like where you realize, wow, I have to analyze, the space ahead of me is when your Battlesnake gets really big. Like you maybe you just didn't expect it to last this long. Like we're over turn 200 here. And 007's doing okay. It's like, I don't know if it's on purpose or not, but circling, I don't know how to use a computer, who is a much more conservative Battlesnake and seems to favor being small. But it's just so easy once you're this length, if you're moving kind of randomly or pseudo-randomly, to just get like tangled in on yourself and run out of space because your own Battlesnake body's in the way. So no, okay, 007 managed to get through that. And did a really smooth head collision there. But like there's so many times where it was such a risk. And I wonder how much like RNG randomness saved them essentially, rather than kind of like a deliberate choice. And you don't want to rely on RNG. Cool. So there's really like one class of fill algorithms, and they all kind of fall down to like the concept of like, imagine you've got like some pixel art and you're using the paint fill can to like fill in a color. It's really that. So let's take a look at this one. Cool. There we go. So like the way most flood fill algorithms are designed is like the idea is that you're like filling in with a different color. And that's certainly not something we need to do in Battlesnake. But it's like an okay concept because the filled in lines indicate the places you can go. So the black are barriers that we can't move through. And the white are the areas that we can go from some kind of like origin. So the core concept here is understanding the difference between like open space versus occupied space. And what this does is like very similar to like how like Dijkstras and A-star works, is it starts from like a starter node. So I would start from your Battlesnake's head, wherever your location is right now. And then it just kind of like moves out in every direction. And there's two common implementations. So this is like the 4-way, which is the most appropriate one for Battlesnake, because you really can only move, up, down, left, right. But there's also, if I pull up a different version, here we go. There's a variant of this algorithm that is 8-way. So same same picture, but diagonals are allowed. So you can see it moves on the diagonal into the spaces where it can. So that's just an important thing to keep in mind. If you're looking at a flood fill algorithm from a library, you want to make sure you're using the 4-way fill and not the 8-way fill, because 8-way is not like diagonal is not a valid move in Battlesnake. You want to use the 4-way. So that's a parameter to tweak. In the Battlesnake case, and this is sort of more just about like analyzing your output from these algorithms, is we don't necessarily want to paint the area, but we do want to know like the count of what was painted, like how much space was there. And at the end of the day, you really just want to see how big it is. And then you can kind of key that on your own Battlesnake's length to give you an idea about whether or not you can fit in that space. So there's a lot, like if I crack open here, I'll just show you because it's easier than trying to just verbally say it all. But if I just go straight to the flood fill Wikipedia page, what you see here is that there's like quite a few parameters. There's like a core algorithm here, and there's quite a few different tweaks to this algorithm that are going to affect the speed and like the direction of travel. So I really love, let's zoom in on this, can I? If I shrink this down and scroll to it. Yeah, there we go. So this is still like 4-way fill, just in a different shape with like barriers in this like fun yin-yang pattern. But there's a simple change in whether or not they like stored the nodes that they wanted to explore in a queue versus a stack. And it changes the way that it kind of expands out, which is quite interesting. So you can see in the stack how you end up with these gaps, right, that don't get filled till later as you move through it, where 4-way using a queue is a lot more uniform, like it spreads out in a uniform manner. And I bring this up because like flood fill can potentially be a little bit expensive depending on how much space you're filling. So there might be like an optimization there and just picking how you're filling. And like what slight tweaks to the algorithm will control the direction so that you can get to your answer a little bit quicker. Because maybe you just run this until you know the space is like one bigger than your Battlesnake size. And then you can stop. You don't have to fill anymore, and that'll save you some time. Another variant, which is kind of fun, to get another animated GIF here. Oops. Get that loading, is what they described. They called this like span fill. So span, as you can sort of see, is like really moving in kind of like a left-right direction. And it has a similar behavior where it will leave gaps, right? Like it's going up as much as possible. So span fill is a neat one. Starting from the seed, you just sort of like focus on filling like left or right first, and then you just kind of keep track of the edges. But one of the sort of downsides of this algorithm is what ends up happening, and you can kind of see it earlier in the draw when it gets around the eye, is that it can mean that it'll visit the same node twice. So it's like it painted over it twice or like counted it twice. So that can be like a little bit of a speed deterrent. So it depends on what your goal is. And this is something, yeah. So in order to fill in between the eyes, it had to like come back. So that's like something that's a little bit of a kind of performance problem. But that would be something interesting to like tweak and compare when you're like building your flood fill. So like flood fill is a very simple algorithm, arguably. I mean, it's used in a lot of, especially graphics applications, but there are a lot of like tiny parameters to tweak and play with. And this might be another example of a fun one to build yourself and to see how you can modify it and change it. Is this stream recorded? Yes. So we record all these streams. It'll be up on Twitch afterwards. And we will also do like a light edit and throw it on YouTube as well. So yeah, if you like want to look at this, or just like, if you're like, you don't want to frantically take notes, but you want to be able to reference this later, absolutely can. It's part of why I'm doing this topic, is I feel it's good knowledge for this early stage algorithm work, right? Like, what are these algorithms that people talking about? Why do I care? How do I find them? So yeah, check this out later for sure. So, I mean, here's Spanfill. Wikipedia, once again, to the rescue, has a lot of pseudocode on how to write these algorithms. So if you do want to do this yourself, lots of great resources, potentially fun for those of us who enjoy spending our time Battlesnake coding. But this is an area where you could like start playing with this yourself, maybe try how this works, see about moving through the nodes and get some practice. Yeah, so here's all of the options, the parameters, our 4-way, our 8-way, popping through this flood fill with the queue and stack version, and then span filling as well. So lots of options, like definitely read these and see what's available to you and what things you want to try. Just really nice, really great options. Walk-based filling, which doesn't have a sweet animation, but just another example of things that you could take a look at and check out from this perspective. Yeah, yay, recording, sweet. Cool. All right. So, I mean, this covers us like quite a few things here at this point, right? Like if you've just started building your Battlesnake and you kind of if-elsing it and you can avoid other Battlesnakes for the most part and you can avoid the walls, but you're really just looking at the next move and you want to start thinking a little further ahead, like a larger plan of going to a specific destination. Well, that's where you can start looking at pathfinding algorithms. Or if you're trying to evaluate whether or not there's a safe space to move into, like if you're moving down a path that's going to take you to a squeeze area, and you want to know that in advance, that's where these fill algorithms can be really helpful. So if you're learning, if you're like early in your programming journey and you're like, what keywords do I need to Google? Pathfinding is great. Pathfinding algorithms, fill algorithms. And as you're looking at the cornucopia of algorithms out there that cover this topic, you specifically want to focus on ones that are tied to grids or graph theory. Those are the ones that are going to help you in a Battlesnake situation because Battlesnake is a grid. Battlesnake is a very structured graph. So those are algorithms that can help you out and you can move through. Cool. So just to kind of like wrap the educational aspect of this, I wanted to talk a little bit about like how I approach these topics. Like, how do you get started? Obviously, watching a video like this is a huge help. But how do people who make these videos get there? And I just wanted to share that like when I learn about algorithms and approaches, I have some strategies that I use. And one of the first things that I do actually every time I need to talk about a Battlesnake topic is I go to a great resource that is available to us all. I'll dump this in chat too. I talk about this all the time because I love it. Let's share my screen again. Yeah, is this GitHub awesome list maintained by community member Hextagon. This is rad. Like, this is just such a good place to start. There's obviously all the Battlesnake resources out there. I love those. I write a lot of those. But these community resources can just be that extra something. So this awesome Battlesnake includes a lot of things. It has links to open source Battlesnakes that you can look at. So if you're looking for examples of people who've built Battlesnakes with specific code, it's here. And there's also great sections about developer stories. So on a variety of topics, whether it's like building a specific Battlesnake, or even there's one on live streaming that was put together from when we first started live streaming Battlesnake tournaments. Obviously links to the game rules and logic. But when you're ready to start diving into like, okay, what machine learning techniques, what algorithm techniques works, there's some great sections here on machine learning and data science, as well as strategies and algorithms. So there's some stuff here I didn't talk about. There's like another kind of fill technique you can use called Veroni, which is like a little bit meatier. I wasn't ready to talk about it on stream without like a whole bunch of studying in advance. But there's a link here talking about that and some different approaches. And once you've exhausted these kind of pathfinding algorithms and these fill algorithms, there's some other really common strategies that start to move into machine learning. And I've talked about these a little bit before in different streams, but things like tree search algorithms like min-max and using alpha beta pruning. These are techniques that people have used and tried in Battlesnake. So we already know that they're useful and have a place. So this is a great place to start. These community resources are fantastic for finding algorithms information that specifically are helpful for Battlesnake. So that is a great place to start. So these are prerequisite. What do you mean by that, Tara Rex? So these are prerequisite. Like, you can do whatever you want. These are just suggestions on areas that you could try to expand your Battlesnake, like things people have done in the past, and stuff you could sort of like learn from if you wanted to see what other people have done as well. But none of this is required. Your Battlesnake is your Battlesnake. Do with it what you will. It's your playground, your personal project to learn about whatever you want as it relates to programming. I hope that covers your question, but if I got that wrong, please just let me know and I'll try to answer it. Cool. So beyond like Battlesnake specific resources like Hexagon's awesome list, if there's like any algorithm that you hear talked about in chat or like you hear about or someone's doing, like honestly hit up Wikipedia, start doing some reading, find out what the name is. There are tons of good blog posts. Oh, data structures and algorithms, is that a prerequisite? So there are like no prerequisites for Battlesnake. You can do what you want. When you're starting your Battlesnake, I recommend if else's and like starting to say like, okay, if my location is, if my head is at X is equal to 0, Y is equal to 10, because that's in like the bottom left-hand corner, you can't turn left because that'll run you off the board. So you can start with if statements to check locations and do kinds of those things. But once you kind of reach the limit of that and you're ready for the next challenge, yeah, data structures and algorithms really help. And if data structures and algorithms are something you want to learn or practice, I think Battlesnake is a great place to practice those things. So not a requirement, but it's an opportunity. Let's put it that way. Opportunity to like learn these things and practice these things. Cool. Awesome. So if you are doing this journey, like if you have seized this opportunity to learn something about data structures and algorithms, you could also write about it. I would be delighted if someone wrote about like their early Battlesnake journey. A lot of these posts on the awesome list are like fairly advanced, if I say so myself. Like there's some here of building like a multi-agent reinforcement learning environment, which is hardly an introductory topic. It's a very interesting topic. There's a lot of people who would be into it, but I would love to see more introductory journeys. Like I tried every pathfinding algorithm that I could think of and compared them. And this is kind of like a neat way that Battlesnake can help you practice more than just your programming skills, is you could practice your writing skills and kind of like build a bit more of a portfolio and write some blog posts. That could be kind of a fun activity, and give that a go and try those like kind of other side skills. And that might be something nice if you're like trying to put together a project for school, or you're like looking for a job application and you wanted to show that you are good at technical writing. This could be a way to practice. And you can definitely make a pull request to the awesome list. It's public, it's for everyone to contribute to, and add that to the knowledge of the Battlesnake community and help the next person be a bit of a mentor to the next person who discovers Battlesnake. So I'd like to offer that opportunity. That's a cool way to learn as well. Learning by doing can be sometimes a little painful and challenging, but is really effective and is an absolutely great way to learn. Definitely my preferred way. I'm terrible at memorizing, but when I do something and I practice it and I write about it, that just helps a huge amount. So that could be an option, just like a new way to explore your algorithm journey and do that. And take it however you want. Like I invite you to find and use libraries that implement these algorithms. They're popular. So you should be able to find one in your programming language of choice. And that is totally acceptable and great. A library function is going to be really optimized, is going to be well tested, and is probably going to work. But if you want a challenge, and if you just want to experience it for yourself, I'd challenge you to write the algorithm yourself and do it inside your own Battlesnake and have that experience and see what it takes to build it yourself. And you'll just develop a really great intimacy and understanding of the algorithm if you build it by scratch. So yeah, and there's no wrong way to do this. Like this is your learning journey. Take it how you want to. these are opportunities I just want to sort of point out that are there for you. So like, yeah, that's like, I think that's my number one message from deep learning is like explore, test things, try stuff, see what happens and see what you find out. You could, try multiple pathfinding algorithms and, just put time into your Battlesnake in whatever aspect you want to practice. Try silly things just to like see what happens. Winning Battlesnake games is like just one part of Battlesnake. I mean, obviously it's a fun part because prizes are pretty fantastic. But there's this whole other part where Battlesnake is about your personal journey and what you get out of it. And that's kind of the other part of the Battlesnake experience that I love. There's the tournaments, there's the excitement, there's the prizes, but then there's also the sharing and the learning and the community. So these are both ways you can help participate. Cool. So unless someone has any questions or thoughts, but that's what I wanted to talk about today. Just give that overview of available algorithms to you. Maybe give a little encouragement if you're in your journey and you want to try stuff. So thanks for hanging out with me for the hour. And thanks again to our partners, AWS, RBC, GitHub. Because of them, we're able to run Battlesnake streams like this. And once again, just a shout out, if you have something specific you'd like discussed on deep learning, let me know. I'm in the Battlesnake Discord, so feel free to pop into there. And if you have done anything you want to show off, maybe practice some streaming, we can do that too. I love doing kind of partner streams and showing off what people have learned and built. This is our chance to like share our messy learning journey with each other, which can be a lot of fun. So if you're excited for more Battlesnake streams, next week, same time as this slot is going to be Joe doing a coding badly. So there's more Battlesnake streams coming in the future. We also have the Winter Classic Invitational coming up. Let me bring up, here we go. If you're not familiar already, I'm just gonna, oops, here we go. So Battlesnake website, play.battlesnake.com. If you start here, pop up that URL, not like you guys know it, you all know it. But if you head to this like calendar icon in the top, brings you to the schedule. And I'm just gonna peek into December a little bit. We can see here the Winter Classic Invitational, which is gonna feature all of the champions of the 2021 season. They are gonna be invited to compete in this special event. So in addition to Coding Badly, which is scheduled for most of the coming Thursdays in December, we also have the Winter Classic. And that's just here on December 11th and December 18th. Hang out and stream, grab a hot cocoa, and enjoy seeing some top tier Battlesnakes battling it out. So those are the things you have to look forward to. Cool. All right. Thanks all for joining me. Enjoy the rest of your day and hope to see you in a future stream. Bye-bye.